The next thing that I'd like to do is measure how bendy a curve is, and that concept is going to be called curvature. So for example, if I have a curve that looks like this, how bendy is that, say, compared to a curve that looks like that? Well, one way to think about that is to look at tangent vectors. So we can look at how does a tangent vector change as I move along a curve. Notice that for this curve, the tangent vector is changing quite a lot as I move through the curve. But for this, yes, the tangent vector is changing, but those changes are more slow. So that's how we're going to develop the concept of curvature. So first of all, we have to think about the tangent vector. And so we're going to recall that if you have a curve, r of t, that the derivative r prime of t is tangent to r of t. And so we're going to define what's called the unit tangent vector. That's going to be the derivative of our curve, r of t. And then we're going to divide that by the length of r of t, or the derivative of r of t. And that's so we have a unit vector. And so then we want to understand how that unit vector changes. And that's going to be our definition of curvature. So the curvature of a smooth curve, that's one where r prime of t is not equal to 0, with a unit tangent vector t of t is going to be given by the magnitude of the derivative of the tangent vector with respect to arc length. So what we're going to do is we're going to measure how quickly the tangent vector is changing with respect to a change in arc length. So this derivative is not dependent on time, because we don't want to define curvature based on how fast a particle is moving along a curve. No, the derivative is with respect to arc length, because we want to understand how that tangent vector is changing as the curve bends. Of course, t, as you see it's defined, is not defined in terms of the variable s. It's actually defined in terms of the variable lowercase t. And so we're going to have to figure out how we can rewrite this derivative in terms of the time variable t. So the chain rule tells us that the derivative of the tangent vector is in fact the derivative of the tangent vector with respect to s, arc length, and then we're going to multiply that by the derivative of s with respect to t. So we're going to think about the unit tangent vector as being a function of arc length, because as you can see, it changes as we progress through the arc length. But then arc length is a function of t. And so we can solve for dt ds in this way. And so we get that dt ds is in fact going to be d capital T, d lowercase t, divided by ds dt. And so that's actually how we're going to define curvature. So curvature is going to be the absolute value of the derivative of the tangent vector with respect to time divided by the absolute value of the derivative of arc length with respect to time. That's going to be our definition of curvature. Again, this looks like it's going to be a difficult definition for us to apply. So what we're going to do is we're going to think about all of our curves as having a parameterization, and that parameterization is going to be r of t. So, in fact, the curvature of a curve given by r of t is going to be r prime of t cross r double prime of t, and then divided by r prime of t in absolute value cubed. Now that seems like that's going to be a mysterious formula, so I'm going to justify that to you. Okay, so let's start. So first, let's note that the tangent vector was defined as r prime divided by the magnitude of r prime. And we can think of the magnitude of r prime as being the derivative of arc length with respect to t. So before we showed that if we integrate the magnitude of r prime, that would give us arc length s. And so the derivative of s is therefore the magnitude of the arc length. Okay, so then another way that we can write r prime, given that definition, is we can think about r prime as being the magnitude of r prime times the unit tangent vector. So what we're saying here is that vector r prime is its length times the unit vector that's in the same direction. Okay, but the magnitude of r prime is going to be ds dt, and then we have the unit tangent vector t. So this is just another way that we can write r prime. What about r double prime? What is that? Well, that's going to require us to use the product rule. So that's going to be the second derivative, d squared s dt squared times t, plus, now I'm going to leave ds dt alone and take the derivative of the unit tangent vector. So I'm going to get t prime. Okay, so now that I know what r prime and r double prime are, I'm going to ask myself, well, what is r prime cross r double prime? That seems to appear in our formula, so what's that? Okay, well, that's going to be the cross product of ds dt t with d squared s dt squared t plus ds dt times t. So now I've got to take that cross product. So the cross product with a sum of two vectors is going to distribute. But something I want you to be aware of is that the ds dt's and the d squared s dt squareds, those are scalars, so they're going to come out. So I'm going to get ds dt d squared s dt squared times t cross t plus, now ds dt times ds dt, or ds dt squared, and then this is going to be t cross t prime. So when I wrote this line just above, I forgot a prime. Okay. Now, what is t cross t? What is the cross product of a vector with itself? We know those are parallel, so that cross product is 0. And so r prime cross r double prime is just ds dt squared times, t cross t prime. Okay, so let's look at the magnitude now. So the magnitude of r prime cross r double prime, what is that going to be? Well, it's the magnitude of ds dt squared. And then it's also the magnitude of t times the magnitude of t prime. There's supposed to be a sine theta there, but these two vectors, t and t prime, are going to be perpendicular to each other, so that sine theta is going to be 1. And in fact, we also know that the magnitude of t is 1, because that's a unit tangent vector. So this is just going to be ds dt squared times the magnitude of t prime. But the magnitude of t prime is exactly what we're looking for in our definition of curvature. Okay, so look here and you'll see that the magnitude of t prime appears in our definition of curvature. Okay, so what is curvature? That curvature, which is kappa, is going to be the magnitude of t prime divided by the magnitude of ds dt. The magnitude of t prime we can get by solving for t prime in this equation here. So the magnitude of t prime is in fact r prime cross r double prime divided by ds dt squared, and then that whole thing gets divided by ds dt in magnitude. And so this becomes r prime cross r double prime divided by the magnitude of ds dt cubed. And the magnitude of ds dt cubed, that is the same thing as r prime of t cubed, as we saw here. And so now I have justified this formula for curvature. And so this is a more practical formula for curvature that we can use. So let's look at an example. Our example is going to be to find the curvature formula for a space curve r of t, which is going to be cosine t, sine t, and 0.1 t. Actually, I'm going to make a small change right now. So we're going to actually do cosine t, sine t, and t at a general point. So this is the helix curve that we have looked at before. So in 3D, it looks something like this. Oops. Okay. And we want to find the curvature formula for that curve. So in order to do that, we need to find the derivative of r of t and the second derivative of r of t. So r prime of t, in this case, is going to be negative sine t, cosine t, and then the derivative of t is 1. And then the second derivative is going to be the derivative of negative sine t, which is going to be negative cosine t. And then the derivative of cosine t is a negative sine t. And then the derivative of 1 is 0. And so now I need to take the cross product of r prime and r double prime. So that's I, j, k, negative sine t, cosine t, and 1, negative cosine t, negative sine t, and 0. Now you're familiar with cross products, so I'm not going to go through all of the details, but I will tell you that this is going to be sine t, and then we're going to get a negative cosine t, and then 1. Okay, so we need the length of that vector. So the length of r prime cross r double prime is going to equal the square root of sine squared t plus cosine squared t plus 1. So sine squared plus cosine squared is 1, so that gives us the square root of 2. And then, remember, we're going to divide that by the length of r prime of t cubed. So we need the length of r prime of t. That's going to be the square root of sine squared t plus cosine squared t plus 1. So that's going to be the square root of 2. And so kappa, which is our curvature, okay, is the length of r prime cross r double prime divided by the length of r prime cubed. So that's the square root of 2 divided by the square root of 2 cubed. And so that's in fact 1/2. So the curvature of this helix that we've looked at before is in fact 1/2. Okay, now let's look at what is the curvature of a circle. So a circle is going to have a parameterization r of t. It's going to have a radius a. So it's a cosine t, a sine t, and the derivative of r of t is going to be negative a sine t, a cosine t. And then the second derivative of r of t is going to be negative a cosine t, negative a sine t. So again, we're going to want to find r prime cross r double prime. So we need to do cross product I, j, k of negative a sine t, a cosine t, and we're going to put that in 3 dimensions, so we're going to give a 0 there. And then negative a cosine t, negative a sine t, and 0. And so if we do that cross product, there in fact is not going to be an I or a j component. In fact, there's only going to be a k component for this cross product. And so we're going to get a squared sine squared t plus b squared cosine squared t times k hat, if you want to specify it that way. Okay, sorry, not a b squared there. A squared cosine t squared t. And so a squared sine squared plus a squared cosine squared is going to give us a squared in the k hat direction. It makes sense that this cross product is only going to be in the k hat or upward z direction because our circle we're going to think about as being in the xy plane. And so that means that that when we take the cross product, it should only be pointing up. Now, we're going to do the magnitude of that as well as, so the magnitude of r prime cross r double prime then is just simply a squared. Okay. And then the magnitude of r prime of t on its own is going to be the square root of a squared sine squared t plus a squared cosine squared t, which of course adds to a squared, so it's the square root of a squared, which is a. And so kappa, like we've seen before, is the magnitude of r prime cross r double prime over the magnitude of r prime cubed. So that's going to be a squared over a cubed, or 1 over a. So the curvature of a circle radius a is in fact 1 over a. So what this says is the larger the circle, the smaller the curvature. So you can think about if we have a small circle, okay, so a small tight circle like that, right? Then the tangent vector is going to change very quickly as we move around the circle. But if we have a large circle, well, then the tangent vector is going to change a lot more slowly as we move around the circle. So the larger the circle, the less curvature that we have.